And today I'm going to talk about a bit about my PhD work, which is focused on the ionic-electronic transport properties of tin-based perovskites. So the content of this talk will include a bit of introduction to tin-based perovskites, and I'm going to strongly focus more on tin lead compositions more than pure tin. And also I'm going to talk a bit more about the basics of ion migrations, which ions are moving, what's happening when these ions move in terms of the device performance and stability. And then I'm going to give more details about all the measurements I actually use to quantify this ionic electronic transport. And then finally, I'm going to provide some conclusions of my work. Tin-based perovskites, and in particular tin lead perovskites, I think are really interesting because when you start mixing tin with lead, you can reach band gaps around 1.2 EVs, down to 1.2. And that enables basically an IR absorption, which can be really interesting for single junction and multi-junction perovskite solar cells. So let's say you want the ideal band gap for a single junction, which is around 1.3 EVs. Then for that, you will need around 30 to 40% tin around this region. And if you're looking more for multi-junction devices where you need a narrow bandgap absorber of around 1.2 EVs, then for that you will need around 50 to 70% tin. And because of that, I would say that tin lead perovskites have seen an increase and rapid development in terms of their efficiency. The 50% composition nowadays, after basically 10 years, now has reached 24.1%. Which is really close to other technologies like silicon or pure lead perovskite solar cells. So the potential is there, of course. However, as the same as with lead perovskites, we also suffer a lot from stability. And I think this was summarized very nicely by the work from Rosales, that he talks about the Gibbs free energy of these materials and comparing the perovskite with different semiconductors. And for instance, you have the oxides that have a really negative Gibbs free energy, which means that if you see their chemical equation from reactants to products, that means that basically oxides likes to be products. They're really stable as products. However, perovskites are near zero Gibbs free energy. So that means that basically perovskite can go very easily go back to the reactant sides of the equation. So they are not really stable. And one kind of a bit of an exaggerated example is this triple junction device that was reported last year. And then you see that when you have a device like this under real conditions like VOC, 85 degrees, light, and ambient air, you see that a decline of the efficiency that occurs really, really fast. And many degradation mechanisms can be happening at the same time. For example, photo-oxidation. This is very important, for example, for wide bandgap perovskite, where you have mixed halide compositions. You oxidize the iodide, and that iodide can be the driving force for halide segregation. You can have electrochemical reactions. Again, the iodides may react with the contacts on your device. Perovskites are overall known for this low defect formation energy. So you can have a lot of defects created very easily. And then they are also sensitive to ambient conditions, especially to water, to oxygen. They can have phase changes. For example, they are all inorganic perovskites. They can convert really easily from this stable black phase to the yellow phase. And then some of these components can be volatile, such as methylammonium. And when we talk about tin lead perovskites, I think the most important aspects that contribute a lot to their stability is this low defect formation energy and their ambient sensitivity. In our lab, we have investigated, for example, the degradation mechanism of a tin lead perovskite, and it's actually really similar to a pure tin perovskite, where oxidizes the tin 2+ to tin 4+, forming TinI4. And when this TinI4 reacts with water, it forms HI as a byproduct. This HI can be oxidized again with oxygen to form iodine, and this iodine can again oxidize the tin, forming this cyclic degradation. So ultimately, what limits the stability of these materials is basically going to be oxygen and water. But this is kind of some good news because we can avoid this degradation pathway by good encapsulation techniques, right? So if we have encapsulation that is compatible with these systems, then you can avoid the most dangerous species that can degrade your perovskite. So we were questioning what other factors could limit the stability of a tin lead perovskite solar cell. And we found in the literature that the composition of the A side cation matters a lot. We did a review a few years ago, and then we analyzed different devices from different reported results. And then what we see is that basically when you have methylammonium in your perovskite, you can have consistently high efficiency systems, all right? But when it comes about the stability, again, this is a figurative metric called T80, which is basically, well, T plus 80 kind of, which refers to the time it takes to degrade 80% of the initial efficiency. You see that different compositions like cesium Fa or triple cation, when you have reduced amount of Ma, are the ones that are more stable. So one of the first lessons we learned from the literature is that the A-site composition seems to be related to a trade-off between this efficiency and stability. Another interesting thing we observe is that the whole transport layer also matters a lot in terms of stability. The typical selection of a transport layer is P.PSS, as you see this in chart 5. Basically, like 60% of the reports we review use P.PSS for high efficiency systems. However, again, when you see the most stable devices, there are other alternatives like PTAA or HDL3, some SAMs, and also P3CT has been raised as a potential stable HDL. Another lesson learned is that if you actually see the most stable device of thin-depth perovskite solar cells so far, which was reported back in 2019, they use these so-called ion blocking layers, or materials that are basically more resistant to iodide corrosion. And so what they did is basically they removed the BCP, they do tin oxide, which is nowadays fairly common practice now. And they, instead of using the typical metal contact, silver or copper, they sputterize though. So even if you have these ion blocking layers back then, and not so many people were looking into the ion transport properties of thin perovskite. So it was really an aspect that is overlooked. And another interesting aspect of this device in particular is that even if it's the most stable device, it's not using fancy additives except for tin fluoride or any passivant. So that might be also indication that, for example, some passivants might not lead to really great stabilities. So in this talk, I will just focus on this third point, and I want to understand better how these ion transport properties occur in tin-based perovskites. And so we know that the defect formation energies of these materials of perovskites are really low. And this is one of the main reasons why you have a migration of ionic species. So the most common defects that you're going to find in a perovskite are related to the vacancies. And one of, for example, the lead vacancy has actually a relatively high activation energy, around 0.8 to 0.3 electron volts. And the reason of that is because if you actually want to move a lead iodide towards a vacancy, you actually need to break a lot of iodide bonds with the iodides. So that's energy demanding. In terms of tin, actually, you have a lower activation energy, and that is related to the fact that tin can oxidize to tin 4+, which is a smaller cation, and then doesn't fit into the lattice. So it's easy to remove this this ion. Then the vacancies of A-site cations are around, the energy is around the formation energy, so it's around 0.4 to 0.8 electron volts. And then the lowest formation energy you find is related to the vacancies of the halides, which is around 0.1 to 0.6. And that is because basically the iodides have to travel really short distances towards another vacancy, to an adjacent vacancy. And also the movement of the iodides can be stabilized by the dipole of A cations like methylammonium or formamidinium. So when people refer to ion migration in perovskites, they probably are talking about iodide migration. And so what happens when ions move in your device is that eventually they will accumulate at the interfaces. And once they're in the interfaces, several phenomena can happen. And one of these is that they can change the built-in potential. So for example, here you have the Venn diagram, and you see without any ions, right? So you have the conduction band, and then you see this nice slope, which is basically related to the built-in potential, right? So the ability to extract charges out of the semiconductor. But when you have a high ion density, that these ions will accumulate at this interface, and then you see basically that the nice slope that you have here in your conduction or your valence bands disappears, becomes flat. And that means that you basically are reducing the built-in potential or screening the built-in potential inside your semiconductor, which is going to affect how efficient extract charges out of the system. And this is probably the most popular example of this screening of the built-in potential is the hysteresis effect, right? So when you calculate the efficiency of your device through a JV scan, things like the scan direction or the scan speed matters a lot. And another thing that can happen is that with time, the ions can react with contacts or within the perovskite, and that can affect definitely the stability of the system. And also in another recent paper from Jarla and Professor Stolteford, they basically quantify how many ion losses you have during photostability experiments, and basically most of the losses you see are related to mobile ions. So understanding this ion migration is really important in perovskites. Sorry about that. And so when I started looking into ion migration in thin perovskites, I found that there was still a bit of debate on how this was happening, because we have basically two views. One of the views was that you have less ion migration when you have tin. And so one of the theories to explain this was that you basically have a stronger bond between the tin and the halide than the lead and the halide. So since you have a stronger bond, you basically lock in that iodide so it cannot move around the lattice. Then another report they also mentioned that it's not so much about the tin halide bonding, but it's more related to the defect, the tin vacancy defect. And as you can see here, this ion migration barrier between different tin, lead, and lead compositions, it doesn't really change a lot. But when you consider the effect of the vacancy, this barrier increases significantly. And the reason of this is because basically when you have a tin vacancy in the lattice, your lattice is already distorted. So if you start moving iodides through this lattice, it's going to distort even more. So that's very unfavorable for energetically speaking. So that's why it increases this migration barrier. However, there were also results that suggested that actually you have a significant amount of mobile ions in tin perovskites, around 10 to the 17. And this amount of ions can lead to significant losses in your short circuit current. As well, there are other examples, many examples out there actually, where they show that you actually have a lot of hysteresis in this type of materials. And for example, in this particular one, they use cesium to reduce the hysteresis in your materials. So it was still kind of debatable how this ion migration occurs in tin perovskites. And from our experience and from other research out there, we know that the chemistry of tin really impacts the electronic transport in perovskites. From here on the right, you see this plot that basically shows the conductivity of different tin perovskites. And when you have pure tin, you have basically 8 orders of magnitude higher electronic conductivity than with lead. And that's because basically any process related to the oxidation of tin via oxygen or iodine, it creates holes. So that p-dopes the material. Also, if you have a tin 4+ and you reduce this tin 4+, it can also lead to a p-doping effect. And also, if you have vacancies related to tin, these tin vacancies act as basically acceptor states, which p-dopes the material. So we know that tin content has a huge influence in the electronic transport, but it's still not clear how the tin influences this ion transport. And so we started by, we wanted to quantify the ionic conductivity in these materials with a technique called galvanostatic polarization. This technique was actually pioneered by Professor Joachim Meyer's group. And this technique, basically, you have a lateral device with symmetrical contacts. And in this device, what you do is you basically apply a constant current to this device. And then you track the changes of voltage versus time. All right. So basically what you have is that in the early time, you see this kind of logarithmic dependence of the voltage with time. And then it reaches a plateau, a constant behavior. So at this region, you have what is known the mixed conduction. And then after the plateau, when you reach this plateau, you reach this electronic conduction. So let me explain to you a bit more in detail. So when you start the measurement, you basically have ions and charges randomly distributed, and then you start applying the current. Then all of these ions and charges will basically contribute to create ionic currents and electronic currents. So the total conductivity of your system will be defined in terms of this electronic and ionic conductivity. After some time, ions will start to accumulate at the interfaces. And so basically you're gonna start reducing the amount of mobile ions that effectively influence the ionic current. So what you will see is that the electronic conductivity will start to dominate the total conductivity of the system, because basically you are reducing the ionic conductivity. And then at some point, you will deplete all the mobile ions available. So basically all the conductivity that you're gonna measure is gonna be only the influence of the electronic contribution. So if you calculate the conductivity at this time near zero, you're gonna have the total conductivity of the system. And if you calculate the conductivity at this point, you're gonna have the electronic conductivity of the material. And then from this, you can easily reduce the ionic conductivity. And one of the actually big problems we found with this measurement was the selection of the metal contacts. For instance, when we use silver, what we see is that we observe this polarization curve. However, every time we took the measurement, we got different curves, right? So it was not a reversible process. And also we try with gold, pure gold, and what we see in the first cycle, we observe this polarization curve that the voltage increase and then starts to decrease significantly. And then in the following measurements, this voltage decrease, which was not the expected behavior. It should stay relatively constant. And so what we did is we thought that there might be some chemical reaction between the contacts and the perovskite, and we tested with chromium. Chromium has been known to be more inert to actually react oxidation with iodide. So it's way more stable than other metals like gold or silver. And we found that you can get more reliable measurements when you use this combination of electrodes. If you actually extract the electronic and the ionic conductivity from the different measurements we do, they are really similar in terms of the magnitude. And we look a bit deeper into this, and we actually saw that when you polarize these are samples after a galvanostatic measurement. And when you have the gold electrodes, for example, you see these white particles on top of the surface. And even if you go to near the middle of the channel of our films, you see these also the white particles. And this is an unbiased electrode. So these particles occur after you bias these materials. And in contrast, when you have this chromium gold combination, you see that actually the electrode kind of degrades a bit. You see also these particles here, but overall you don't see the same amount of density of these white particles, and also near the middle of the channel you can see this effect. So we believe that when you have only gold, you might see actually gold migration into the perovskite, which basically induces artifacts in our measurement and incorrect can lead to big errors in the measurement. So with that once we decided that this chromium gold was a better electrodes for our measurements, we started our measurements, and this time we basically fixed the A side composition, and then we tried different compositions of tin, from basically lead to pure tin. And what we observe is that in all cases, we see this polarization curve. All of them show this ionic-electronic behavior, regardless of the content of tin. However, the magnitudes do change. And so, for example, these are the electronic and ionic conductivities extracted from all samples. And basically, we have 3 observations from this. The first one is that when the tin content remains equal or lower than 50%, actually the ionic conductivity is bigger than the electronic conductivity. And this is kind of expected, since lead perovskites also show a similar behavior, really consistent to what Professor Myers observed. Then the second observation is that when you have really high content of tin, now the electronic conductivity starts to dominate the ionic conductivity. And again, this kind of makes sense, considering that when you have a lot of tin, you will have a huge carrier concentration. So you basically, the electronic conductivity will overcome significantly the ionic one. And the third observation is that these 2 quantities, electronic and ionic conductivity, seem to be related to each other. because basically they follow exactly the same behavior with the tin content, both increase at the same time or both decrease at the same time. So we were wondering if these quantities were related, right? So if you see the definition of electronic conductivity, they basically depend on the charge of the electron, the Hall mobility, and the carrier concentration. And the ionic conductivity also depends on the mobility of the ion, the charge of the ion, and the mobile ion density. And so we wanted to establish if there was any relationship between these two. And also, importantly, we needed to consider that the reason why the electronic conductivity in tin perovskite is so high is because you have a lot of tin vacancies, right? When you have these tin vacancies, you have a lot of holes that will influence the electronic conductivity. This is been already proved. And so we were wondering as well if the tin vacancy actually also influences the ionic conductivity as it was previously suggested. However, to actually prove this, if these three quantities are related, we couldn't do this with this experiment. And the reason of that is because we need to think about how ion transport occurs in these materials. And that's the way it happens is basically through grain boundaries, right? People have proposed different models where ions move through the grain boundaries of perovskites. And so the shape of the grain, the size of the grain, the density of grain boundaries, the crystallinity, all of these things matters a lot. And when you start changing the content of tin, well, you change all of these aspects in your material. So for example, here you have the SEM figures of different concentrations, different films with different concentrations of tin. And you see that basically all of them are changing significantly. So it is really hard to pinpoint the effect of ion migration to just the tin ion, or it's more because you're changing the morphology significantly of your material. So it's very hard to deconvolute the effect, right? And so we had an idea to use tin fluoride. And tin fluoride is a very nice additive that can actually modulate the number of tin vacancies in your material. And the idea was that you can use this, instead of changing the composition, you fix the composition, but you change the concentration of tin fluoride, which is going to change the concentration of tin vacancies. And the way it works, basically, tin fluoride has been proved that captures the impurities, the tin-I4 impurities in your material by forming tin-I4 and the tin iodide that is actually in the oxidation state that you wanted. And so if you increase the concentration of tin too close, you increase the chemical potential of tin, and you end up decreasing the formation energy of these tin vacancies. And so the nice thing when you fix the composition and then you just change the concentration of tin is that you don't affect morphology as significantly as changing the concentration of tin. And so we compare, for example, also with XRD, the different shifts in the peak of the 100 peak. You see here the black line corresponds to the tin when you change the tin fraction, but when you have the tin fluoride, it remains relatively constant. Also, the full width have maximum of the 100 peak remains relatively constant, while the one from the tin fraction changes significantly. And grain size, we do see an increase in the grain size when you start adding tin fluoride, but again, it's not as crazy as when you start changing the tin fraction. And so maybe this is a limitation for our study, but I would say it's the best we can get. And so when we try to measure the electronic conductivity and the ionic conductivity as function of the tin fluoride concentration, and what we found is that electronic conductivity goes down, which makes sense. You are decreasing the number of tin vacancies, you're losing the number of Hall carriers in your system. But again, the ionic conductivity seems to follow the same trend as the electronic conductivity. And so with these experiments, we kind of show that also tin vacancies can modulate the ionic conductivity. However, we were also wondering still if there was a connection between the ionic and the electronic conductivity, as then again, they followed exactly the same trend. And so more in particular, we were wondering if there was a relationship between the carriers and the mobile ions. And so we estimated also the mobile ion density with a technique called low frequency capacitance voltage measurements, which is a technique that has been proposed by Jonas Dickman and Professor Stolteford. And this technique is based on the fact that the capacitance of a perovskite device at low frequencies increases dramatically. You see here this capacitance versus frequency curves. And then when you have a frequency around 10 10 hertz or 1 hertz, you see this step increase in the capacitance. And with drift diffusion simulations, they have shown that the higher the mobile ion density, the higher this increase in capacitance you have. And basically what they propose is that you have accumulation and depletion layers of ions that modulate the capacitance of your device. So basically the higher you have, the more ions you have, the higher this accumulation or depletion layers will be. And now if you apply a voltage at a low frequency that can modulate the movement of ions, then you will modulate this capacitance in your device. And so they propose this equation, which is really similar to a Mott-Schottky equation, where you see the inverse of the capacitance squared. And if you plot this this kind of relationship of the inverse of the capacitance squared versus voltage, and you calculate the slope of these values, you can actually estimate the mobile ion density. And so we did that again with the same experiment. We fixed the composition and then we just changed the tin fluoride concentration. And what we observe is that the mobile ion density decreases as well. We also confirmed that with another technique, which is bias-assisted charge extraction, that was done with the help of Professor Martin Stolteford, and basically confirms exactly the same trend that the mobile ion density is decreasing with the increase of tin fluoride. And also in terms of the magnitude values, they are really close to each other. So now putting everything together, basically we put the ionic and the electronic conductivities as a function of tin fluoride, and also the carrier concentration and the mobile ion density. The carrier concentration we calculated with high frequency Mott-Schottky, very similar to the Mott-Schottky of the low frequency, but at high frequency. And so what we observe is that, yeah, the ionic and electronic conductivity are modulated by the concentration of tin fluoride, but also the mobile ions and the carriers are modulated by the tin vacancies. So basically with this, we kind of prove that all of these variables, the mobile ion density, the carrier concentration, and the vacancies in your system are related to each other. We also visualize if this effect can be observed with PL. And we set a sample without tin fluoride, and then we basically track the PL changes versus biasing time. And then you see the sample without tin fluoride, where we expect more ion migration. You see that a quenching in the middle of the channel occurs after 10 minutes. And this quenching, we attribute it to basically you create a very defective regions. Ions go towards the interfaces. And then in the center, you basically leave a lot of defects, which act as non-radiative recombination centers, which reduces the PL. And when you have a bit of tin fluoride, you would expect a bit less ion migration. So we observe a more stable PL behavior with time. Furthermore, we wanted to identify which mobile ions are moving, because in tin perovskite, I think that was an aspect that was not still very clear. We did a TOF-SIMP ion mass spectroscopy. So what we did is basically we analyzed a film before and after biasing, and we did a kind of like a chemical mapping of this material. And what you see here in these plots, it's kind of like a cross-sectional view of our device. And then you see that the samples, when you don't have the tin fluoride, more ion migration, they show a preferential accumulation of iodide fragments after biasing. While the samples with 5 mole % tin fluoride, we do not observe this preferential accumulation of the fragments. And also interestingly, we see accumulation of organic cations on the other negative electrode without the tin fluoride, while the samples with tin fluoride behave more, we have a bit of less accumulation. So this kind of indicates that we might have a lot of iodide migration, but also interestingly, we can see a bit of migration of the cations, which is formamidinium in this case. We tried to come up with a theoretical model to explain these observations. And what we did is we studied the migration barrier for iodide migration under 4 different scenarios. In the first scenario, you just have the iodide migration, which we call the pristine. Now we wanted to observe what happens when you have a tin vacancy. Then we wanted to understand what happens when you have a positive charge in there. And then what will happen when you have tin vacancies, which are balanced by the positive charges of the holes. And what we found is that, yes, tin vacancy actually only increases the barrier, which is in agreement to what other people have observed. But however, when you consider the charges of the holes, you see a drop in the energy barrier for iodide migration. And we propose that basically a tin vacancy, since this tin is going to be acting like an acceptor state, you're going to have a local positive charge around this area. This positive charge can basically stabilize the movement of the negative charge from the iodide. And then finally, we also study what implications have this in the bias stability of tin-led perovskite solar cells. And what we found is that when you have a sample without tin fluoride and you bias it with 1 volt for 60 minutes, you see basically a really sharp decrease in the efficiency of the device. You lose a lot of the factor, you lose a lot of the JSE. And importantly, we do not observe that after recovering the device for 60 minutes, we do not see any recovery of the efficiency. However, when you have a 5 more % tin fluoride, we also see a decrease in the efficiency, a bit less. But the interesting thing is that actually this device can recover almost to the initial efficiency after 60 minutes of that recovery, which is kind of summarized in this figure. So basically, we propose that this combined effect of vacancies, hole carriers, and on the ion transport basically limits the bias stability of these materials. So some of the conclusions is that basically ion migration in tin-based perovskite is not negligible. It's happening and it's affecting the stability of these materials. And we propose this combined effect of tin vacancies and holos that can modulate the ion transport in this class of materials. Of course, in terms of bias stability, it's going to be mainly driven by ion migration in these systems. And this is really important because tin-led perovskites have this tendency of self-p-doping. So I think it's going to be really critical for the development of stable tin-led perovskite solar cells. And another outcome, I think, is that we need to start studying additives or processing techniques that actually can favor grain growth. Maybe Kai can tell more about this. And also, it will be really important to basically select inner contacts that do not react with iodide or that are stable towards iodide migration. And I think that would be really important to enhance the operational stability of these materials. Just finally, I would like to thank my supervisor, Professor Dario Baran, Dr. Luis Huerta, who have supported me a lot during this research project, and also to all my collaborators from different institutions as well. Thank you so much. And also to all my lab mates back at Omega Lab. Thanks a lot. And of course, thanks to you for all your attention.